Today? I thought you meant early, not late. Wait, everybody's doing it?
Yeah.
Yeah.
We voted.
They said though moving Friday to Monday wasn't good enough.
No, Monday because James moved our other test to Monday.
I would have all three on Monday. So
Well, have her with her test.
No, she moved it because we missed a day because she had jury duty. So it
Yeah.
wasn't because we had too many tests, it was because she had jury duty. So we
Well,
were
I missed a
behind.
day because I was JOs.
You didn't miss it.
I did. I missed a Friday.
Oh, you did.
Remember the
Yeah,
whole
because
time?
that Monday is the
Just more
Yeah.
flexible.
you more go with the flow.
Yeah.
Oh yeah, we have a final paper.
All right, reductions, oxidations. There's quite a bit of work here. The reduction reactions are easy. The oxidation reactions, however, are difficult. I'll show you what we can get away with. And we're going to end up doing some exceptions rather than the main thing. Carboxylic acids, aldehydes, and primary alcohols all live on the same oxidative particle. Oh, that's leaking hot water. I have to fix that. Okay. From left to right, we're performing oxidations. From right to left, we're performing reductions. Okay, here's what we know. Lithium aluminum hydride takes the carboxylic acid, makes the aldehyde, that aldehyde immediately converts to the primary alcohol. Our reducing agent is an H minus. Therefore, all of our reactions come in two stages. One, we do the reduction. Two, when you read the lab directions, it says adjust the pH until the pH of the solution is ever so slightly acidic. And you go, okay, well, I'm just going to follow those instructions. Well, the instructions is because your product cannot be isolated because it has a negative charge in it. When we get rid of the negative charge by neutralizing the solution, making it ever so slightly acidic, then we get our alcohol out. Okay. If we do this, the aldehyde gets made, but not isolated. And we'll find out later that aldehydes are more reactive than carboxylic acids, and also more reactive than alcohols. So they're kind of stuck. If at some point during the reaction, either going this way or coming that way, I have alcohol, aldehyde, and carboxylic acid in solution, the aldehyde's the first thing to react. So we don't isolate it if I use the powerful reducing agents. If I use sodium borohydride, I can reduce an aldehyde. Again, that would be part 1. Part 2 would be acid worker. Sodium borohydride will reduce aldehydes to alcohols. Lithium aluminum hydride will do that reaction as well, but we choose not to use it because it's so powerful it does other stuff as well. Okay, so we limit ourselves. What's missing is a reducing agent that will take the carboxylic acid and stop at the aldehyde. And this clearly is something that would be economically useful for us, because if aldehydes are the reactive thing in the middle here, and we can't isolate them, then that might mean that they're scarce. And scarce resources are the ones that we pay money for. So there is a reducing agent here called dibal, D-I-B-A-L or D-I-B-A-H, depending on which book you read. And again, that will be in 2 steps. And that is di-isobutyl aluminum hydride. And this reducing agent stops at the aldehyde. So now we have 3 group 3 based reducing agents. NABH4, which we use to convert aldehydes and ketones into alcohols. Aldehydes get converted into primary alcohols. If this were a ketone, it would get converted into a secondary alcohol. We have dibal, which converts carboxylic acids into aldehydes. And then we have lithium aluminum hydride that reduces absolutely everything. Okay. In the way up, I have a couple of oxidizing agents that I can use. If I use potassium permanganate. Potassium permanganate oxidizes primary alcohols to the aldehyde and then immediately to the carboxylic acid. Aldehyde's more reactive than the alcohol. It's also more reactive than the acid, and therefore it is now the reactive intermediate in this multiple step reaction. And you might remember at some point from general chemistry what reactive intermediates look like. You've got multiple steps in your mechanism, and one of them has a reactive intermediate, then that reactive intermediate never shows up in the rate law because it just gets consumed quickly. This is potassium permanganate. What was the oxidation state on that manganese? manganese 7. If you have a high oxidation state, that means that you are not likely to be oxidized yourself. You are, however, likely to become reduced, and in doing so, you will oxidize your surroundings. 7 is about as high as you can get. It's not really easily conceivable to think about anything being higher than 7. Because to be at 7, that's potassium, calcium, scandium, titanium, vanadium, chromium, and then manganese. You're halfway across the periodic table at that point. There are 2 other oxidizing agents that do just what happened here. We have permanganate, KMNO4-. We have chromate, CrO4-2-. And then we have dichromate, Cr2O7-2-. All of these are very, very powerful oxidizing agents. You put them in a tiny bit of acid and they rip through whatever it is that you're looking at. So that's manganese in the +7 and chromium in the 6. When your material that you're looking at has a very high oxidation state itself, chances are it's an oxidizing agent. So if I wanted to turn the aldehyde into a carboxylic acid, I'd use anything. Any of these, they would all go. However, if I wanted to turn my alcohol into an aldehyde, I'm stuck. Because if I used any of these, they make the aldehyde and then they immediately go to the acid. And that's not, if I want the aldehyde, I'm out of luck. So we've invented something else that goes here. PCC or PDC is pyridinium chlorochromate or pyrid. Now let's do the C. And what this does is it stops at the aldehyde. If we take a look at the oxidations a little bit closer, we have a second problem. In the world of our oxidations, primary alcohols go to an aldehyde. And then aldehydes go to carboxylic acids. Secondary alcohols go to a ketone. But there is no oxidative pathway above a ketone. There is no oxidative product for a ketone, only the aldehyde. Because remember, we have to lose an H and gain an oxygen. And the ketone doesn't have any more H's to lose. So there's nothing to go here. This is where we're going to be spending some attention. Plus, that's impossible, so we should do that as well. This is difficult, so let's do that. And then this is impossible. Let's go do that as well. So the primary alcohol to the aldehyde, we've already seen that we can do that with a kind of a bulk reagent. I can do that with PCC or PDC. And then from the aldehyde up, well, I can use whatever I want. To go from a secondary alcohol to a ketone, well, why not just hit it with the strong thing? Right? There's no, I don't have to worry about it. I don't have to worry about this because once it gets the ketone, it stops. There's another little tricky reaction though that we can put in here. And a Swern oxidation, we're going to start having lots of Germanic names with W sounds that are pronounced as V's. We're going to see one on Friday called the Wittig, spelled with a W. And today we're going to see a Swern, spelled with the W. The Swern oxidation does this first step. You could take a secondary alcohol, do this fancy oxidation. It's going to require a little bit of effort and some fancy chemicals to make the ketone. So why would you, when the stockroom's already full of KMNO4 and it's cheap? Okay. Don't do the difficult reaction for a simple answer. Turning a secondary alcohol into a ketone is a simple task. We can do it with any of the bulk oxidizers, potassium permanganate, chromate or dichromate. We don't go and do something technical, the Swern oxidation, but we could. Its utility is going to be, I'm going to be able to get an aldehyde. And then, there's a reaction here. Called the Bayer villager. And the Bayer villager is one of very few ketone oxidations out there. It's not the only one, but there's very few. Oh, we're trying one. In lab, I'm writing a new lab for you. Benzoic acid, and then can I do a bleach? Hey. All right, let's do some of the mechanism for this. So good. We're not going to do it. I'll show you why. If you were all chemistry majors, we would be doing it. But you know. That's the mechanism for it's called a Jones oxidation, chromate oxidation of primary alcohol. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 steps. Yeah, okay. It's a thing of beauty. we won't be doing. So these are called Jones oxidations. Let's do some of the other stuff instead. Let's do the Swern, and let's do the Bay of Villages. The reducing agents are all, it's just H minus. Reducing agents are really straightforward. It's H minus. It's nucleophilic addition of H minus, followed by acid workup. It's already been on the board. So we don't have to do anything fancy with those. The hard work is on the oxidation side. Okay. Let's look. What do I have? Jones oxidation. Here we go. Let's do the Swern. Swern oxidation turns primary alcohols into aldehydes, which is useful. It turns secondary alcohols into ketones, which is not. That is not useful, because I have something easier and cheaper that will do that reaction for me. I don't necessarily have something easier and cheaper to do to make the aldehyde. All right, our conditions. I need DMSO. We've seen DMSO before. Now, conversations about the correct solvent to use in an SN1 versus an SN2 conversation. DMSOs were revealed to be polar, but aprotic, just like acetone, and therefore good candidates to do SN2s. DMSO is actually a lousy solvent. It is widely used as a solvent for biological reactions, but it's terrible because it has such a low vapor pressure. You're never going to be able to evaporate it off. Plus it stinks. Plus, I don't know if we've got any in the lab. If we have any in the back room, we can do this. If you take a beaker of DMSO and you put your finger in the DMSO, you can taste the DMSO. It crosses the blood barrier. It crosses the membranes into your bloodstream. It's a drug delivery agent. We're going to use this funny little molecule, C2O2Cl2. And I'm going to use some triethylamine. Okay. Let's do the mechanism. Now, the mechanism occurs in two steps. The first step is to make the reactive intermediate, the reactive species. And in order to do this, I need the oxalyl chloride and the DMSO. That's dimethyl sulfoxide. That's my DMSO. It's a liquid. It's got a bit of a smell to it. You can tell it's got sulfur in it, but it smells a bit burnt as well. And then this is my other reactant. And it is the acid chloride of oxalic acid. This is called oxalyl chloride. All right. Let's look what we have. Reactions come from areas of high electron density and they go to areas of low electron density. What can we see on the board? I see several pi systems. They would be areas of high electron density. And anything else? What about the CLs? Oh, those are leaving groups. We build them in on purpose to be leaving groups. Okay, so glad that we can see the leaving group. My nucleophile is right here. My electrophile is right there. It has a leaving group, but the carbon to chlorine leaving group bond is not the weakest bond in this molecule. The pi bond is. So when I attack that, it opens to here first. All right, now I'm going to figure out just what I did. I made a sulfur. I've skipped a step. Like that. Oh yeah, that makes sense. My electron density comes from the pi bond. So these electrons reach out and grab that carbon. Okay? Now, if that happens, this oxygen, which had no charge, because it has two bonds, in my next sketch, will still have two bonds. Because the pi bond left, and those two electrons went from making an oxygen to sulfur bond to making an oxygen to carbon bond. So, okay. That pi bond breaks. Here's a trick, because we're going to get tired of doing this. That pi bond breaks, and then reforms and kicks off the leaving group. Now, if that happens, and there's a chloride floating around the solution, because that was my leaving group, and it's got a negative charge, well, doesn't that mean that there has to be a positive charge in this molecule somewhere to counterbalance it? On the sulfur. Sulfur and oxygen are in the same group. The sulfur has two bonds, you should expect it to have no charge. If the sulfur has one bond, you should expect it to be negative. If the sulfur has three bonds, you should expect it to be positive. So I've got this thing right here, and I'm going to resolve that charge by using nucleophile, electrophile. Okay? If I attach the chlorine to the sulfur, this is all just prized to fall apart. Because look what I can do. If I can take those electrons and build another double bond to that carbon, I can make a carbon dioxide. And then this breaks apart here. We end up making, this is the thing that we want. This is what's going to be doing the reaction in the next step. I'm going to make a carbon dioxide, a carbon monoxide, excuse me, and a chloride. This is my reactive intermediate. It's called dimethylchlorosulfonium chloride. Might be counterbalanced with that. Name is completely unimportant. But that's our reactive intermediate. This is the reactive thing that's going to be doing step 2. Because the alcohol hasn't even shown up yet. I need either primary alcohol because it's going to make an aldehyde, or a secondary alcohol because it's going to make a ketone. So here's step 2. Step 2 is the actual oxidation. All right, give me a primary alcohol. Make it bigger. Okay. Primary alcohol. Reactive intermediate. Figure out where the area of high electron density is. Figure out where the area of low electron density is. And have one reach out and grab the other one. Where's my arrow going to come from? Okay, where's it going to go to? To where the positive charge is. So we know that the arrow is not going to be generated from this molecule. It's going to be generated from this one. So all I have to do is identify where the electron density is in this molecule, in the alcohol. Where is that? On the low pair of electrons. Good. So the oxygen reaches out, grabs the sulfur. It's going to kick off that chloride. What stage do I have to show these hydrogens? Not just yet, soon. Okay. Got a positive charge here. I've got a chloride there. Anything else that you think I need to have in this molecule? Leaving group just left. The leaving group left is chloride. My oxygen, which was 2 bonded, is now 3 bonded. And if I'm in group 6 and I have 3 bonds, I need a positive charge. I also need a positive charge on the sulfur. Yes, I had something leave, but I also made a new bond to it, so there's still a positive charge there. What I did was generate a new separation of charge, that plus and that minus. They cancel each other out. I still have to go back and find the positive that was in this sketch, and it's still on that oxygen. Okay, first thing we're going to do, get rid of that proton from the oxygen. That leaves me only the one positive charge in my molecule now, because the other positive charge has just floated away. Here's where the other reagent comes in, because in the first step, I've taken my DMSO, my oxyl chloride, and my alcohol. Technically, if we split it this way, what we could even do is split one is DMSO and oxyl chloride. Step 2 is the alcohol plus this, which is really from here. And then step 3 I need a base. So I'll call this step 3. Could be step 2 if you just count everything that's happened up to this point as being step 1. All right, step 3 is triethylamine. Triethylamine is a base. It's a mild base. It's a liquid, and we use it in lots of also biologically relevant reactions again today. As a base that can also be used as a solvent because it's a liquid, and it just mops up stray protons that are around. But it's going to take this hydrogen right here. One pair of electrons on that nitrogen. Takes that hydrogen. And what that hydrogen does with its electrons is it just gives them to the oxygen. The bonding set of electrons that were in a carbon to hydrogen bond are now in a carbon to oxygen double bond. Well, that oxygen already had 2 bonds. If you make a new bond to it, it has to give something up. And it gives its electrons back to the sulfur as a lone pair of electrons. And that gets rid of the positive charge. So I just made an aldehyde. And I turned my DMSO into DMS, which is dimethyl sulfide. And turning DMSO into DMS is something that happens from time to time. And when it does, we should all be aware of it. But it also account for that base is now frozen. All right, there you go. There's my aldehyde product. DMSO, where are you? Right here. Is used as a solvent. It's also used as a drug delivery agent. DMSO degreases your skin and allows itself to cross into your bloodstream. So I said if you put your finger in it, you can taste it because it's now in your bloodstream. If you put a drug in the DMSO, then you can also now administer that drug topically. If you had skin cancer and you wanted to administer the drug to tissue, you could dissolve it in DMSO and then apply it, and it would go where it's supposed to go. Versus taking the anti-cancer drug orally and having that drug now be in every cell of your body. Because anti-cancer treatments usually work by being toxic to the cells, but hopefully preferentially more toxic to cancer cells than to regular cells. So if we can take it and be topical with it, that's good. There is a case, and it's 20 years ago now, that a woman was brought in on a gurney to the emergency room, and the nurses who were treating her, one by one, started collapsing. And then all the doctors that came to the nurse's aid also started collapsing. And everybody that touched this woman fell over unconscious. She was a cancer patient, and she was taking such a high dosage of DMSO that her body somehow had managed to make a significant amount of DMS. And DMS is a nerve agent. So she's excreting DMS, and it's knocking all of the healthcare workers out. We don't necessarily have to worry about DMSO. If you have cancer, it will help you not have cancer. Of course, if you don't have cancer, it will help you get cancer. If you are not poisoned, it will help you get poisoned. And maybe under the right circumstances, if you are poisoned, it will help you get unpoisoned. Okay, so that can happen. Only really useful to make the primary alcohol to be aldehyde. You could get secondary to ketone. Just change your ethanol for 2-propanol and do the exact same mechanism. It's the same thing. Okay. The beta villager oxidation does something curious. It turns an aldehyde plus a peroxy carboxylic acid into carboxylic acid and another carboxylic acid. That is a peroxide bond. An oxygen to oxygen single bond is a peroxide. If at the end of your reaction that single bond is still intact, you've done it wrong. Does that say it's still recording?
Yeah, it's slow.
Okay. If this bond is still intact, you've done it wrong. This is a very weak, unstable bond. That must be broken. Let's be a bit more specific. The oxygen is going to migrate out of one of these molecules into the other. Now, we already know that aldehydes and carboxylic acids are at the ends, alcohols and carboxylic acids are at the end of an oxidation pathway. This has more oxygen than this. This has one oxygen, this has three oxygens. This has two oxygens and two oxygens. So 1 plus 3 equals 2 plus 2. This is a special type of redox reaction. Anybody know what it's called? Anybody know what it's called when you have two molecules of the same thing and then they split apart and they make one that's higher in oxidation and one that's lower in oxidation? That's a disproportionation. Heard that word before? No. It's the opposite of a disproportionation or proportionation. It's a comproportionation. Here's the trick. Oh, I'm out of time. Pick you up some. No, Friday. Test on Tuesday. If you want it on Wednesday, you can have it on Wednesday.
It will really get graded. I don't think it will say.
Not Monday.
So Wednesday.
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 What did you call
You
it?
didn't want to know.
I just asked.
I played pretty